Hi and welcome. This is the first video of a series that I'm planning to release, which is about something that I have been studying and I wanted to share with you, which is about metric space topology. On this video, we will work some basic terminology and also cover about finite and infinite sets. And for this series, I will be using a book that that I've been using to study this subject, which is called Real Variable Variables with Basic Metric Space Topology. And this book is from the author Robert B. Ashe, which contains 9 topics, 9 chapters, very well developed. So we will be using this book for this first approach to this subject. Okay, let's get straight to the topic 1.1.1, which is definitions and comments. So the union of two sets A and B denoted by A union with B. So this symbol that we'll be seeing with very often is called union. Is the set of points belonging to either A or B. And the intersection of two sets A and B denoted by A intersection with B. So again, this symbol we will see with very often and is called intersection. It means the intersection of two sets. Which is the set of points belonging to both A and B. So maybe and probably you might already have saw these symbols because it's very often used even in high school content because it is the basics of set theory. And now let's introduce this other concept, which is complement. So the complement of a set A denoted by A to the C is the set of points not belonging to A. Okay, and all this content um, that I'm writing, I'm talking from the book. And we will be working in a fixed space omega which is sometimes called universe. So maybe you are used to to see omega as a set or as a big set of other sets, but right here this omega for us it means a space and space, and all sets under discussion will consist of various points of omega and thus a complement is the set of points of omega that do not belong to A. Okay, now to represent the sets, we got something called Venn diagrams. So let's see. So let's say we got a set of A and a set A and a set B. And we wanted to represent the union and the intersection between these two sets. So those are different sets its union and is its intersection. And again, this is something that probably you have already saw because it's something that is taught in school, in the high school. So its intersection sorry, its union first, and the union, as we saw, the definition is the set of points belonging to either A or B. And the intersection again, which is the set of points belonging to both A and B. Okay, and unions and intersections might be defined for more than two sets. In fact, an arbitrary collection of sets So for example, the union of sets A1, A2, and so on, denoted by A1 union with A2, or we can use this other terminology, which is a union of a set which is the set of points belonging to at least one of the A1. So notice that right here we are introducing this new information, this I indexed, and this I pretty much means the collection of all possible indices. So index set which is the collection of all possible indices So for example, if we have this index set I equals a set with the elements 1, 2, and 3, and let A1 be the set with the elements A and B, and let A2 be the set with the elements B and C, and let A3 be the set with the elements C and D. Then we can say that is union of this I set belongs to A with this I set, which is equal the elements of each set. So I is a way to keep track of which sets we are referring to. Okay. The intersection of A1, A2, and so on can be denoted by, which is denoted by A1 intersection with A2, now can be denoted by the intersection symbol and this I index, A I index, and again I is a way to track of which set we are referring to. And this is the set of points belonging to all the I index I, sorry, A index I. And also we can write a infinite sequence of sets. So the union and for that we need a way to represent these infinite sets instead of write, for example, A1 union with A2 union with A3 union with A4 and so on. We need a way to represent these infinite sets. So the union of sets A1 to AN and right here this index, and it means a infinite number of sets as you wish. A number of sets as you wish is often written as a union, and right here I index starting from 1 and going to infinite. So a union of A starting from 1 going to infinite. Sorry, I'm skipping this. Of course, is n infinite. So this is for infinite sequence of sets. Okay, so this is for a finite sequence of sets. And now we can represent with this same terminology, but only changing the upper limit. Now we need to change the upper limit for infinite. If you wanted to represent an infinite sequence of sets, a union, of course, a union of finite sequence of sets and a union of infinite sequence of sets. And just getting back a little bit right here, I forgot to represent using the Venn diagram a complement set. So a complement using Venn diagram is this way. So a set A, and outside of the set, which is the points that do not belong to A, so right here, points that do not belong to the A set. Okay. There are a few identities. There are a few identities involving unions, intersections, and complements that come up occasionally. And let's start these identities. The first one is the distributive identity. Sorry, uh, the identity, it will come up by this distributive law. So with the distributive law, this identity will come up. So A intersection with B, with the union between B and C is equal. Now applying this distributive law, so the intersection between A and B, the sets A and B, union with the intersection between the sets A and C. So by applying this distributive law, this identity will come up. Okay, and distributive because intersection behave like a ordinary multiplication. So intersection behaves like ordinary multiplication. And union behaves like an addition. And actually we can verify this identity using the Venn diagram. So we got a set A, a set B, and C. So first, a union, sorry, the intersection of the set A with the set B. In a union with the intersection between the set A and the set C. So let's say got this intersection between these sets. So using the Venn diagram, this is the set which is A intersection with B in a union with A intersection with C. And now we can write that if x, a point x, if ax, a variable x, belongs to A in an intersection with a union between B and C, then x belongs to the A set, and x belongs to an intersection between the sets a union between the sets B and C, so that x belongs to B or x belongs to C. So this is an assumption. And for that, we got two cases. So in case that x belongs to A and x belongs to B, then x belongs to an intersection between the sets A and B. Hence, x belongs to A in an intersection with B in a union with the intersection between the sets A and C. On the second case, x belongs to A and x belongs to C. then X belongs to an intersection between the sets A and C, hence X belongs to a set A intersected with a set B in a union with the intersection between the sets A and C. Okay, so what we are trying to demonstrate with this assumption is that on the left, this set right here, on this left side of this identity, so let's call set of the left, and set of the right. So this set on the left is a subset of the set on the right. Okay. Okay, and for that we can use a Venn diagram to represent this subset relation. So now we can write a set D and a set E, and this is a subset relation. And now the set D is said to be a subset of the set E if every point of D also belongs to E. And if right here we are using this logic to say that the set on the left side is a subset of the set on the right side, so in order to write that D is equal E, which is the equality of sets, to prove that D is equal sorry, we need to show that D is a subset or is included in E, and E is a subset or is included in D. Sorry, the right way to read this is that D is a subset or is included in the E set, and E is a subset or is included on the D set. And if D, which is a subset or is included on the E set, but the set D is different of the set E, we say that D is a proper subset of E, and we can write that D is a subset of E, and we can take a conclusion of this um, according to the definition a set is a subset of itself. Okay, and now let me just copy this Venn diagram. With these unions, intersections between the sets A, B, and C. So to return to the proof, of the distributive laws, suppose X belongs to an intersection, a union between the intersection of A and B. So the set A intersection of the set B with the set B in a union of the intersection between the set A with the set C. Then we can say that X belongs to A in an intersection with B, or X belongs to A in an intersection with C. The set A in intersection with the set C. Thus, we know definitely that X belongs to A, and also X belongs to B, or X belongs to C, as desired. Okay. And all this was from this first identity. So this was our first identity. And now we got, let me see, three more. We got two more identities. So the following identities call it the De Morgan laws. Are often useful. So this is the second identity that we can verify using De Morgan's law. So a set of A in an intersection with the set B, its complement to the C. So we can read this as an intersection between a complement between the intersection with the set A and B. So an intersection A intersected by B complement to the complement, which is equal A complement in a union with B complement. And right here I wanted to do a analogy with the Boolean logic. So De Morgan, it can be used for this theory of sets and also in Boolean logic. And Boolean logic is something like that. So something that I wanted to call your attention is that you can use this analogy if in some point you got difficult to understand what we are doing with the symbols of intersection and union. So in Boolean logic, we got this A and B in this certain of operation of multiplication, but actually is operation that is called AND. So AND B, and we got this bar right here. And when we apply this bar on each of these elements, we change this operation of AND. So this operation right here, which also a analogy to the operation of multiplication. When we apply this bar on each of these elements, we change this operation for this operation of R. This is R, this is and this R is analogous to the operation of sum. And right here is the same. Notice that when we apply the complement on each set, we change the symbol of intersection by the symbol of union. And we can verify this identity using the Venn diagram. So we got these two sets, A and B. Inside of this subset, so A complement in a union with B complement, and this is A and this is B, and this is the intersection. So any point on this subset, on this complement, belongs to the set A and B. And okay, if the left side is a set and the right side is a set, the conclusion that we take right here is that a set is a subset of itself. Okay, and we can also write that A in a union with B to the C. Applying the De Morgan's law, we verify that A complements in an intersection. We verify that this is equal to A complement in an intersection with B to the complement. So A to the C intersection with B to the C. And from this second identity, we can write the third one, which is for extend to an arbitrary collection of sets. So an intersection and with this I in index, which means an arbitrary collection of sets is a whole family of sets A I indexed to the C, and applying De Morgan's law, we verify that this is equal to the union of a family or a collection of sets I of A to the C. And we verify the same right here, that for a union of an arbitrary collection or family of I sets, A indexed I to the C is equal to applying De Morgan intersection in an arbitrary or collection or family of I sets of of A index I, a family of sets, a collection of sets to the C, its complement. And this is the formal method to write an arbitrary collection of sets or family of sets, because we cannot use we cannot use the Venn diagram to approach large collection of sets. So this is the formal method to write a family or collection of sets. Now, to end this first part of terminology, we need to introduce the empty set. So actually this was the set theoretic terminology. Now the empty set. And this is the symbol for the empty set, which is the set with no members. So if A is a set then empty is a superset included subset, I said super, sorry, a subset included in a rewrite that a family of A sets intersection with a family with other family of A sets or collection is said to be equal empty whenever whenever I is different of J. So this means that it doesn't have a correspondent element on the set. Now a practical example. As an example, let A be the set with the elements 1, 2, and 3, and B the set with the elements 1 and 2, and C the set with the elements 3 and 5. In this case, the sets, they are not disjoint. So the sets are not disjoint. If you can notice, on the set A and on the set B, we got the elements 1 and 2 correspondent. So these elements, they are correspondent between the sets. And on the set A, we got the element 3, which corresponds to the element to on the set C. So these elements, they are correspondence between the sets. And although we said that these sets, they are not disjoint, although A is in an intersection with B in an intersection with C, and that is equal an empty set because of this element 5. We do not have a correspondent of this element on the C set, on the A, and on the B. So the element on the C set, there does not have a correspondent on the sets A and B. Although we said that an intersection between these three sets is empty. But yet, For we said that they are disjoint. They are not disjoint because of the correspondence between these elements. We said that they are not disjoint, and for disjointed, we must have A in intersection with be equal to A in intersection with C be equal to B in the intersection with C be equal empty set. Again, we said that they are not disjointed because we got a correspondence of elements between the sets. So the elements on the set A, 1 and 2, they are correspondent with the elements 1 and 2 on the set B. And on the set C, we got the element 3 correspondent with the element 3 on the set A. But although we said that the sets A, B, and C, they are empty, its intersection because of this element 5, which does not have a correspondent on the sets A and B. And for disjointed, we must to have the set, the intersection of the set A and B be equal to the intersection with of the sets A and C be equal to the intersection of the sets B and C equal to an empty set. And now using the elements of the sets, so A in an intersection with B. So I will copy the sets with its elements. Okay, so A intersection with B is equal to 1 and 2, which is different of a empty set. So we said that this is not a disjointed. They are not disjointed because they are intersected, and we can prove this with this correspondent of elements of the sets, and they are not empty. also a intersection with C. We got the element 3, which is correspondent. So the element 3 on the set A correspondent to element 3 on the set C. And because of this, we said also that the subset of the sets is not empty. Now, B intersection with C. So, as you can see on the set B, we got the elements 1 and 2, and on the set C, we got elements 3 and 5. So we do not have a correspondence of elements. So right here we can say that the intersection between the sets which will form a subset is a empty set, and a subset is a set of itself. And right here we say that is B and C are disjoint. Right here are not disjoint. And now, to close this first section, the set theoretic difference between A and B is defined by A and this slash reversed slash, which is equal a variable x which belongs to a omega space so x belongs to, and as on this space omega we got the sets A and B. So is the sets on the space. So x belongs to A and x does not belong to B. Which is equal to A intersection with B complement. And this is easy to prove using the Venn diagram. see, maybe right here, something like that. Okay, and with this, we close this first section, and on the next video, we will start to solve some problems, some examples. So for now, it's all. I hope you like it, hope you enjoy, and thank you for watching. See you in the next video. Thank you.